So what we have left to do is two other graphing techniques. One of them is, if you know the original function, what happens when you put that function in your denominator and do the reciprocal of it? And the other one is, if you know the original function, what would happen if you put it in absolute values? That's what we have left to do. And I have some extra handouts for you so that you don't have to write all of this out. But first of all, you see there in the notes that the reciprocal graph does not mean the inverse. So in functions, if you write the -1, that isn't an exponent. That -1 means the inverse. And this is on your notes, so you don't have to write it down. But basically, just like the square root graph, where in a square root graph, all you were doing was square rooting your y values. And then we looked for patterns of which points were important. The same thing's going to happen with reciprocal graphs. All that's happening is you have your original graph, you think about the coordinates on your original graph, and your y value is going to be changing to 1 over your y value. And although this is super simple, it does create some interesting graphs that are quite different. And some of you have already recognized in doing your exam reviews that this was one of the things that you ran into that you're like, have we done this? The answer was no, but we're going to do it today, and it should make sense. So here's the simple idea. Any point on your original graph will change to 1 over y. But some interesting things happen. First, how are we going to go about doing this? Well, we're going to draw our original graph first. And steps 2 and 3 are going to result in asymptotes. And you've actually seen this idea already. If you had a non-permissible value in chapter 2 with reciprocal graphs, that non-permissible value either ended up as a vertical asymptote or a hole. With reciprocal graphs, it's going to always end up in a vertical asymptote. So wherever your original value had an x-intercept, 3, 0, when you change the y value to 1 over its previous y value, you would get 1 over 0. And 1 over 0 is not allowed. So we're going to draw a vertical asymptote. In chapter 2, with your rational graphs, you had 3 things to look for to find out if there's going to be horizontal asymptotes or oblique asymptotes. So a quick review of that. If the degree was bigger in your numerator than your denominator and you didn't cancel out to get a whole, that was an oblique asymptote. If the degree was the same in your numerator and your denominator, then you had a horizontal asymptote at the coefficients of that highest degree. And if the degree was bigger in the bottom, then you ended up with a horizontal asymptote at y equals 0. In reciprocal graphs, we're going to play off that idea a little bit, because sometimes you're going to get polynomials, like an x squared. If you have a 1 over x squared graph, you will say, hey, I could use chapter 2. The degree is bigger in the bottom. I'm going to have a horizontal asymptote at y equals 0. But we're also going to have some equations like 1 over log x. And you have a log on the bottom. And that doesn't really have a degree. But the idea is if your original graph either goes, so if your original graph either goes to positive or negative infinity, okay? The y coordinates go toward positive and negative infinity, then you will have a horizontal asymptote at y equals 0. Because what it's saying is if your y values keep getting bigger and bigger and bigger, when you do 1 over them, they will get smaller and smaller and smaller and approach 0. So steps 2 and 3, when drawing your reciprocal, you're going to draw your original graph first. Then you're going to draw asymptotes. Do step 2 and 3 together. And then steps 4 and 5, I will just, beside steps 4 and 5, I will refer to steps 4 and 5 as nice points. If you have a nice point on your original graph, 2, 4, then all you have to change is your y value to 1 over it. So 2, 4 will change to 2, 1 over 4. And you can do that to as many points as you'd like. And just like in chapter 2, we're going to, at the end, draw our graphs towards our asymptotes. So I also handed out to you a bunch of examples. We will do these together. In the notes, I did like very slowly through the steps, but I'm going to redo it how you would do it if you had the same question. Okay? So here's our first example. You want to graph 1 over x squared minus 4. In fact, this could have been a chapter 2 question. This is review. You could do this one already with chapter 2. But using our new technique, the idea is you will first draw, and I'll draw it in blue, x squared minus 4, which is just a parabola moved 4 units depth. And I can actually label quite a few points on here. Right? It's easy to label points on that original graph. In graphing the reciprocal, and I'm going to graph the reciprocal here right beside it, the first thing I'm going to do is graph asymptotes. So, for graphing asymptotes, we're going to look for vertical asymptotes. Does our original graph have any x-intercepts? Yes. At -2 and at 2. Those will become vertical asymptotes. And in reciprocal graphs, you always have a 1 on the top. Does it make sense that no non-permissible values will ever cancel out? So you will only have vertical asymptotes in 1 over graphs. Every non-permissible value in a 1 over graph is going to be a vertical asymptote. And we can label those as x equals 2 and x equals -2. And we should also do our horizontal asymptote. So this is one in chapter 2, you would say the degree is bigger on the bottom. I know I have a horizontal asymptote at y equals 0. In reciprocal graph techniques, in reciprocal graphing techniques, if your original graph, check this out in green here, do you see how this keeps going up and up and up, bigger and bigger and bigger? If your arrowheads either go towards positive infinity for y values or negative infinity for y values, you will draw a horizontal asymptote at y equals 0. So I call this, if drawing your original graph is step 1, I actually combine step 2 and 3, and asymptotes is your second thing you need to do, both vertical and horizontal. Next, just do nice points. In other words, what's going to happen to 0, -4? It's going to change to 0, 1 over -4. What's going to happen to 1, -3? It's going to change to 1, 1 over -3. What's going to happen to 3, 5? It's going to change to 3, 1 over 5. Oh, I have nothing in this section. So I'm going to find a point here, -3, 5. So now I have -3, 1 over 5. And if you have a point in every section, you can draw your graph towards your asymptotes. And reciprocal graphs, 99.9999% of the time, have no x-intercepts. I will show you the one exception to that today. But it makes sense that the top is 1. And if you have 1 over something, you will have no x-intercepts. Because the top can never equal 0. Which kind of makes you curious, how can there be a 0.0001%? What example breaks this rule? We'll see that later today. But this is the idea. You draw your original graph. You draw your asymptotes. And then you just take every y-coordinate and change it to 1 over that y-coordinate to get new points. Once you've got points in each of your sections, just like you did in Chapter 2 with rational graphs, you draw your graphs towards your asymptotes. In fact, you did this in grade 11. This was reciprocal graphs of parabolas and lines. You did in grade 11. I give this one a name in grade 11. I call it a sad clown face. I don't know why clown. You see the frown? It's sort of like, I don't know. It looks like a sad face to me. Here's our second one. Oh, I gave this one a name too. So you start by drawing your original graph. X squared plus 1. It would have 0, 1. I could label some other points on here. 1, 2. 2, 5. -1, 2. It's easy to label points on your original graph. Then your reciprocal graph. Do you have any x-intercepts? No. No vertical asymptotes. Does our graph keep getting bigger and bigger and bigger? Yes. So we will have a horizontal asymptote at y equals 0. And if you use Chapter 2, can you see the degree is bigger on the bottom on this one? Degree is bigger on the bottom gives you a horizontal asymptote at y equals 0. Now we just need to do some nice points. What's going to happen to 0, 1? It's going to change to 1 over 1, which stays the same. And in our notes, there was like a special thing about points that stay the same. They're called invariant points. Does it make sense? Whenever the y value is 1, or if the y value was -1, when you do 1 over 1 or 1 over -1, it stays the same. But if I do 1, 2, that's going to change to 1, 1 over 2. 2, 5, that's going to change to 2, 1 over 5. -1, 2. So notice your x values are not changing at all. It's just you're changing your y values to 1 over what they were previously. And if we drew this towards our asymptote, this is the final graph. So one of the things that makes reciprocal graphing tricky is we just did the reciprocal of two parabolas, and the final graphs, the first graph and the second graph, are completely different looking, right? I gave this one a name. Did your teacher give this a name in grade 11? Do you remember what we called that one? Speed bump. Doesn't it look like a little speed bump? Awesome. Okay. That's the idea of reciprocal graphs. What the exam, like these first two, were examples from grade 11. So you did this in grade 11, you're expected to do it in grade 12, but in grade 12, we're not restricted to parabolas. We can put anything on the bottom you've graphed already. I can put logarithms, I can put trig equations, I can put square root equations. Anything you've graphed already can now go on the bottom of a function and say, you can graph that as well. So here's the square root graph. Square root of x plus 4. Does it make sense? That's just a square root graph moved 4 to the left. If I want to label points on my square root graph, I've got 3 here labeled already. I could even label another one. What would be easy to label? 5, right? You plug in 5. Square root of 9 is 3. You get 5 comma 3. What does our reciprocal graph look like? Do we have any x-intercepts? Yes. We have an x-intercept at -4, so that will become an asymptote. Think about the arrowhead on the square root graph. Right here. Does it keep going up or does it eventually level out? Does it keep getting bigger? Would you say the range of a square root graph is 0 to infinity? Or would you say the range of a square root graph goes from 0 to, and it stops? There's a certain number it does not get higher to. Does it go to infinity? Yes. Keeps getting, so it keeps getting bigger and bigger. This is enough to tell us there is going to be a horizontal asymptote at y equals 0. So I like to graph my original function first, then I like to do my asymptotes. And then after my asymptotes, now I just look for nice points. So I have -3 comma 1. That's going to become -3 comma 1 over 1. That's an invariant point. It does not change. 0 comma 2. Well, that's going to become 0 comma 1 over 2. What's going to happen to 5 comma 3? All you do is change your y values to 1 over what they were before. 5 comma 3, 5 comma 1 over 3. And in fact, this is enough information for us to draw things towards our asymptotes, and our graph is done. Notice there's nothing to the left of x equals -4, but there was nothing to the left of x equals -4 to begin with. So that should make sense. And a favorite thing that the exam likes to do is draw some weird graph, bunch of straight lines joined together, and say, given that weird graph, could you graph the reciprocal graph? And again, I'm going to do it right beside. Does your original graph have any x-intercepts? Unfortunately, it has 3 of them. It has 1 at -1, it has 1 at 2, and it has 1 at 5. So those will become 3 vertical asymptotes. 1 at -1, 1 at 2, and 1 at 5. Does your graph go up forever or down forever? So I'm going to look on this side, no arrowhead. This side stops. But on this side, do you see that there is an arrowhead pointing up? Which means it's going to keep going up forever and get bigger and bigger. If your graph goes off to either positive infinity or negative infinity, you will have a horizontal asymptote at y equals 0. Now we have to do some nice points. Well, you have -5, -1. 1, 2, 3. You will still have -5, -1. You had -2, -1. That will stay -2, -1. Does it make sense that if you have a flat line on the reciprocal, that will also be a flat line? Even if it was a different number. If those were all 3's, they would all change to 1/3's. And it would be a flat line that way as well. Okay? 0, 1 is going to stay 0, 1. 4, -1 is going to stay 4, -1. And 6, 1. All those are going to stay. All those nice points that were labeled, because if you do 1/-1 or 1/1, it's the same value. Now you have to decide how you're going to draw this towards the asymptotes. And the easiest way is 1/, graphs have 99.999% of the time no x-intercepts. So on this one, I'm getting close to an asymptote. Should I go up or down? I should go down, because if I go up, I'll make an x-intercept. What about this section? I need to go up. And of course, you could pick a point, right? I could pick this point right here. This point is 1, 1/2. Reciprocal means you take a fraction and flip it. What happens when I flip 1/2? I get 2/1. Also tells me this had to go up towards the asymptotes. This section, down towards the asymptote. And there is our final graph. So you saw some of these probably already on your exam reviews. If you left them blank, now you are able to do them. Now they got a concert coming up.